So you are in a project that uses Kubernetes. There you have a dev cluster and a prod cluster. Prod is kept stable, but dev, not so much. And it isn't stable because people use it as a test bed to try things out. Wouldn't it be great if everyone had a cluster for themselves? There they could experiment safely. Well, I have good news. This is possible by running Kubernetes locally. But wait a moment. There are actually so many options. Which of these is the best? What are the strengths and weaknesses of each one? Let's find out together. This video is intended for viewers that have worked with Kubernetes before. Fear not, I'm only assuming basic knowledge. If you know what pods are and kubectl is, then you're good. Sounds good? Then let's go. We'll come back to this overview in just a second. First, I'd like to establish what I'm looking for. Foremost, I want a local throwaway Kubernetes cluster to experiment on. This sounds simple, but has important implications. For one, fast cluster creation or resetting is essential, but it also means that container image storage for the workloads needs to be considered. Just think about it. If recreating a cluster means having to download a gigabyte of data each time, how fast can it really get? Certainly not as fast as not having to download. Second, it should match the feature set a cluster in the cloud would have. Thirdly, reusing the same or a similar setup in CI pipelines would be great. The teams on my project require a way for running integration tests. Spinning up ephemeral Kubernetes clusters is perfect for the job. And finally, it should be cross-platform. In particular, it needs to work well on macOS with Apple Silicon, because that's what I use. Let's have another look at the overview. I've categorized the solutions for running Kubernetes locally into two main categories: standalone solutions that run directly on the operating system, and container-based Kubernetes solutions which require a container engine to run them. But what does standalone even mean here? Well, Kubernetes runs containers, and containers are actually built on various Linux kernel features. So, on macOS or Windows, you need something that provides a Linux environment via some kind of virtual machine. Software that provides this itself is what I call standalone. The container-based Kubernetes solutions are, you guessed it, just containers, so they require that you already have a way to run containers. I also listed Podman. It is standalone, but without built-in Kubernetes. It's just a container engine. It is, however, able to run all three container-based solutions on the bottom. And yes, Minikube is listed twice. That's not a mistake. It's very versatile and offers different modes, or drivers as they call it. So it really belongs into both categories. I'll present more general information about these projects later in the video. But now it is time to put them to the test and compare them. But how? I've come up with 6 challenges. First, we'll create our first cluster and deploy some basic Kubernetes manifests to test the waters. Second, we'll build an image locally and run it in Kubernetes. Third, we'll run an image from a private registry. Fourth, we'll expose a service to localhost, and we'll do it by actually exposing it, not via kubectl port forward. Fifth, we'll look into how convenient and how fast it is to reset the cluster. And finally, we'll run the solutions that support it in CI/CD pipelines. Challenge number 1. First cluster. Let's start with Docker Desktop. After opening the app, we can observe in the status bar that it is starting its VM where it runs the containers. It has built-in Kubernetes, but not enabled by default. It can be enabled via a checkbox in the settings. Less than a minute later, Kubernetes is running. Let's use kns to view the pods running on Kubernetes. Now let's install a workload. I've brought here a simple deployment and a service that serves it at port 80. We can use kubectl apply to install it. The pods immediately show up in kns, and we can also see containers in Docker Desktop's UI. To verify that it is running, we can use kubectl port forward to expose the service at localhost 8080 and then view it in the browser. In conclusion, it is impressively simple to use Kubernetes with Docker Desktop. Next up, Rancher Desktop. Let's open the app. We are greeted with a welcome screen. Here we can select the Kubernetes version and we can choose between 2 modes. I'll choose Docker D mode because It lets me use the Docker CLI to build images. We'll do that in challenge number 2. Let's go. Again, we can observe in the status bar that the system is starting. Less than a minute later, Kubernetes is running. And with kns, we can view the pods. Let's apply the same manifests. Then port forward and we can verify in the browser that everything is working. A handy feature of Rancher Desktop is that it has a built-in dashboard for Kubernetes, in which we can view the pods and the service. At work, I see many developers use the Google Cloud website to view Kubernetes resources. It's great to see an integrated dashboard for the local cluster. In conclusion, Rancher Desktop is just as easy to use as Docker Desktop. It feels even more geared towards Kubernetes because it lets us choose the Kubernetes version and offers a built-in Kubernetes dashboard. I also should mention that while Rancher Desktop is foremost a desktop app, it does also offer a CLI with commands to configure, start and stop it. Now let's look at MicroK8s. Let's open the terminal because MicroK8s offers a CLI. We can use the MicroK8s install command to create a cluster. It first creates a VM and then from within the VM the snap package manager is used to install the components. After about 1.5 minutes the cluster is ready. We can list the pods on it via the MicroK8s kubectl command. Notice the command starts with MicroK8s. It's because the MicroK8s CLI has a built-in kubectl. Unfortunately, I can't use the kubectl or kns installed on my system right away. To fix this, I have to manually update my kubeconfig. Now kns works. We can again install the workload. We use port forward and verify that everything works in the browser. Like Rancher Desktop, MicroK8s offers a built-in Kubernetes dashboard. We can get to it by running the dashboard proxy command. After 1.5 minutes, we are presented with a link and a token. MicroK8s was easy to install and creating a cluster was straightforward. What however baffles me was the kubeconfig, because every other solution I'm presenting today edits the kubeconfig automatically. Also, when accessing the dashboard, I had to click through certificate warnings. Now let's have a look at the container-based solutions, Minikube, Kind and K3D. To run them, we need a container engine. We could use Docker Desktop or Rancher Desktop, but since we've already seen those in this segment, let's use Podman. First, we need to create a rootful Podman machine. The Podman docs tell us that this is required. After the machine is created, we can continue on the desktop app. Just like the other desktop apps, Podman Desktop has an icon in the status bar. Now it's time to create our cluster. Each solution has a slightly different command. Through the magic of editing, we can see them running in parallel. We can use Podman PS to view the container running Kind. Or alternatively, we can also use the Docker CLI because Podman is compatible with it as well. The rest is exactly the same as earlier. Alright, we've seen that all container-based solutions offer a simple CLI command for cluster creation. Later in challenge 5, we'll compare how fast they start on Podman versus Rancher versus Docker Desktop. Finally, I've mentioned earlier that Minikube can run standalone. Also, while it is primarily a CLI, a few weeks ago they also released a GUI. I'm first deleting the existing Minikube cluster. Then I'll create a new cluster with the qemu VM. About 40 seconds later, the cluster exists and we can view it in kns. We'll install the workload again and verify that it responds. And to finish off, I'd like to showcase another neat trick of Minikube. It has, like Rancher Desktop and MicroK8s, a convenient way to launch a Kubernetes dashboard. After roughly 15 seconds, the dashboard opens and we can view what's running on the cluster. Minikube offers various drivers for different environments. Its UI looks a bit basic but gets the job done. Opening the Kubernetes dashboard was really easy. Challenge number 2. Build and run an image. In this challenge we are going to do something that is extremely common. We are going to build a container image and then run it in our local Kubernetes cluster. For that, I prepared an example service. I'll give you the 30-second summary of what we have here. It's a Node.js service written in TypeScript. It offers this one simple endpoint. It can be executed locally via the npm run dev command, including live reloading on code changes. Here is the package JSON. And finally, here's the Docker file. As you can see, there's more than one from instruction. This is called a multi-stage build, and it makes it so that our final image can be more secure by not containing a bunch of unnecessary stuff like a package manager, dev dependencies, and a shell. Security experts call this image hardening. Alright, now let's get it deployed. We'll start with Rancher Desktop. I've prepared this 3-line script. The first line computes the image name. In here I'm using the date command to get a Unix timestamp so that we get a different image name on every build. Next I'm calling docker build to build the image. And in the last line I'm running kubectl apply. The YAML contains again a basic Kubernetes deployment and service. Although this time the image name comes from a variable. Also, something to be aware of, be sure to either use a tag that isn't latest. I'm using, as I said, this tag containing a timestamp. Or if you do use latest, you need to explicitly set the image pull policy to if not present. This is because the image pull policy magically defaults to always if you use the latest tag. Let's run it. The pod starts really quickly because there is no image pull involved. We can have a look at the logs to verify that the service started cleanly. Finally, we can use port forward again and call the service from the browser. And that concludes the demo for Rancher Desktop. Next, we'll have a look at Docker Desktop. I'm executing the same script, and as you can see, everything works exactly the same. Docker Desktop and Rancher Desktop both run Kubernetes directly in their container runtime, and this means we can just run locally built images. Kubernetes does not need to pull the images from a container registry because it already has them. Kind and the other container-based solutions work differently. The big blue box here is Kind's container, and within this container another separate container runtime is running. And that's where all the Kubernetes containers run. This means we can just build a container image on the host and then just copy it over. And to do this, there is a command. Let's run it. And here it is. Each solution's copy command looks slightly different, but they achieve the same thing. This way also works for microcates, however can't say that the command looks very intuitive. In case you're wondering, multipath is the virtualization solution microcates uses on macOS. Anyhow, let's run all of them. As you can see, building the image on the host and then copying it over to the cluster works for all of them. Finally, Minikube can also be used standalone. That means we can build the image on Minikube itself. To do that, we create a Minikube cluster with the qemu VM. Then we can use the basic build script with just 2 lines added. The first line configures some environment variables, the second one enables BuildKit. BuildKit is necessary so that my fancy Docker file can be built. It was enabled out of the box on Rancher and Docker Desktop. And this concludes challenge 2. In my opinion, Docker Desktop and Rancher Desktop were the most intuitive to use. Minikube, Kind and K3D were straightforward. Only microcates involved some weird extra commands, but it also got the job done. Challenge number 3. Run an image from a private registry. So far we've seen how to run a public image and how to run an image that we built ourselves. That's nice and all, but usually every project has its share of private images. That means images you can only pull if you authenticate with valid credentials. And there are lots of private registry options. All the major cloud providers offer them. And then there's GitHub and GitLab, and of course there's also the dedicated artifact storage solutions like Artifactory and Nexus. For today I have prepared a container image on the Google Artifact Registry. To pull it, I first run the configure docker command. As you can see, running this adds a credential helper. Now the Docker CLI can ask for temporary access tokens. We can now pull the image. Since the image is pulled now, we can run it just like in challenge 2. But having to run docker pull explicitly isn't that great, right? With the credentials configured like this, couldn't we just deploy the image and let Kubernetes pull it? Let's try. I have here a deployment that uses this image. and I don't have it downloaded. Let's apply this. As you can see, we are getting an image pull error. This unfortunately doesn't work. Both Rancher Desktop and Docker Desktop could make this work. The Google Creds helper is configured after all, but it doesn't. However, there's a way to make pulling via Kubernetes work, and it is Kubernetes' built-in way. Image pull secrets. The easiest way to create an image pull secret is via kubectl. The command requires a name for the secret, the host of your registry, and a username and password. You can see it created a secret in the namespace. Then in the pod spec we tell Kubernetes to use it. With that in place, pulling from a private registry via Kubernetes works. But the approach that I just showed has two downsides. First, you saw me putting a temporary token into the pull secret. This token will expire in an hour. So in an hour from now, I will no longer be able to pull images unless I update the secret. Luckily, there's a way to fix this, and it is to put long-lived credentials into the image pull secret. In the Google Cloud, those are called service account keys. To create one, Wait a moment, I'm getting a call. Yes?
This is CISO. We do not tolerate service account keys within our organization. They are not permitted there.
The second downside is that we had to deploy and modify Kubernetes resources. In particular, we have to deploy the image pull secret once per namespace, because it is namespace scoped. Usually on the cloud, the permission system of the cloud can be used to authorize access to a private registry without involving any image pull secrets. Let's take a look at some alternatives. The first one is Minikube's GCP Auth add-on. Let's create a fresh Minikube cluster with the add-on enabled. And then we deploy the workload from a private registry. As you can see, it was able to pull the image. But how? What happened? What happened is actually quite clever. It's actually implemented using just image pull secrets. We can see that there is an image pull secret per namespace that was automatically created. If I decode what's in it, we can see that it contains just temporary OAuth tokens. It uses the Google Cloud credentials on the host to automatically create the secret, and it takes care of refreshing it periodically, so it always contains valid access tokens. The other part is it automatically injects the image pull secret into the Kubernetes pods. An excellent solution, right? Now, wouldn't it be great to have a similar solution working on Docker Desktop or Rancher Desktop? Unfortunately, Minikube's solution cannot be easily transferred. Also, writing a Kubernetes webhook to achieve this functionality is quite difficult, or at least tedious. Luckily, it's 2023 and there's now tools to make this easier. I'm going to do it via Kyverno. Kyverno is a Kubernetes policy engine. We can tell it using two policies that it should take care of copying the secret into every namespace and to inject the image pull secret into every pod. It basically takes care of all the complicated bits. I have put this solution into an easy-to-use bash script. Just run it. Here you can see it takes care of the image pull secrets. It will also refresh them automatically. Now pulling from the private Google registry works. You can see our pod has the pull secret. Since all of this is just a bash script, I'd imagine it's also not terribly complicated to adapt it for other cloud providers. The link to the code is in the description. Feel free to use it in your projects. Finally, I'd like to present an extremely lightweight solution for getting image pull credentials into a K3D cluster. Just create the cluster with the following configuration and it will be able to pull the image. The keen-eyed among you will have observed that I'm again using a temporary access token and there is no renewal mechanism here. But that's typically not an issue with K3D. K3D is most useful in continuous integration. There, the cluster doesn't have to live that long anyway. In conclusion, there are multiple ways to run private images. You can load them like in Challenge 2, use image pull secrets, use Minikube's GCP Auth add-on, or K3D's config. Challenge number 4. Expose a service to localhost. In this challenge, we are going to look into how Kubernetes services behave on local Kubernetes clusters. Usually, there is per cluster at least one service of type LoadBalancer. This service is usually for some kind of ingress gateway that you have running in your cluster. How it normally works in the cloud is that you create the service of type LoadBalancer on the cluster and then the cloud provider automatically provisions an external IP address and an external load balancer. The question is now, how does this translate to local Kubernetes clusters? There is of course no cloud provider, and we don't want an external IP either. Let's see how it behaves on Docker and Rancher Desktop. Both handle services of type load balancer in the same way. They expose them on localhost, which is great because developers are very used to this. Let's check it out. The service and the deployment are the same as in challenge 1. Let's apply it. Docker Desktop is on the left and Rancher Desktop is on the right. You're observing again the magic of editing. Once it's deployed, we see here these services. In Docker you see localhost in the external IP column. On Rancher Desktop it's this weird other IP. Regardless, both services are now reachable in the browser on localhost. Very convenient indeed. Next, let's check out K3D. It also supports a service of type load balancer. However, because K3D is running in a container, this setup looks a bit differently. We have to map the port 80 inside of the container to port 80 on the host. We need to keep this in mind when we create the K3D cluster. Let's try it out. I'm first going to create the K3D cluster with the port argument configured. I'm also not deploying the traffic ingress gateway because it also wants to use port 80. Then we can use the same manifest as before. Once it has rolled out, we can check using the browser that it indeed worked. I just want to mention that what we just deployed actually looks like this. It's because K3D supports multi-node clusters. The link with more details is in the description. But now let's have a look at Minikube. Minikube does support services of type load balancer in some manner, but it is a bit weird. Let's deploy the same service again, but this time to Minikube. As you can see, the service remains in a pending state. To get it out of pending and working, we can run the Minikube tunnel command on the terminal. Then the service gets exposed and we can now access it in the browser. This feels a lot like kubectl port forward. Rancher, Docker and K3D didn't require an extra command like this. Fortunately, there's another way that Minikube, Kind and K3D support to get a service exposed on localhost. It is using a service of type NodePort. Host port 80 is this time mapped to 30,080. The NodePort number is so large because it has to be within a certain port range. Here is the updated YAML. What's different is the type and the NodePort field. We can now create the clusters. Note that these terminal windows did not run at the same time. After the manifest is deployed and the pod is running, let's quickly have a look at the services. We can see the created service is indeed of type NodePort. We can again verify using the browser that it indeed worked. Finally, let's look at how microK8s works. I have here a microK8s cluster to which I have already deployed the service of type NodePort from before. We can reach it by finding out the IP at which the microK8s VM runs by running microK8s config. Now I can enter this IP plus the NodePort into the browser and the page opens up. Alright, let's sum up challenge 4. Docker Desktop, Rancher Desktop and K3D are able to deploy services of type load balancer. And all of the solutions are capable of deploying services of type NodePort. This is great to see. microK8s was again difficult to use. Rancher Desktop and Docker Desktop were the easiest to use. Challenge number 5. Which can reset the fastest? It's time to get some numbers now. Let's find out which solution is the fastest to reset. Docker Desktop and Rancher Desktop both offer a reset button. So for those two, reset means clicking this button. For microK8s, K3D, Minikube and Kind, reset means deleting the old cluster and recreating a new cluster. microK8s technically has a reset command. However, my test showed that it doesn't delete everything on the cluster. After the reset, the cluster still contained a bunch of terminating workloads, and I found the service that I had deployed previously to it still on it, not what I call a reset. Also, since I mentioned previously that Rancher Desktop has a CLI, Currently, the CLI doesn't offer the same reset command that is offered on the UI. Hence, I'm clicking the button manually. The testing procedure works as follows. I'm timing how long it takes to reset the cluster, reinstall the basic workload from challenge 4 and wait until it responds. My benchmark is just continuously running curl until a status code of 200 is received. After that, the next test iteration begins. Each solution gets 5 iterations, or rather 6 because I'm always discarding the first iteration. Thus, solutions that employ caching and avoid redownloading content get awarded for it. Also, it reduces the likelihood that fluctuations in network speed affect the results. Additionally, I also configured kind K3D and Minikube with registry mirrors to avoid redownloading the container image of the workload. The link to the code is in the description if you're interested in the details. Docker Desktop and Rancher Desktop Kubernetes don't need registry mirrors. Resetting them doesn't lose the downloaded images. Docker, Rancher, Podman and MicroK were each configured with 5 CPU cores and 8 GB of memory for these tests. The tests were conducted on a MacBook Pro with the M1 Pro Apple Silicon processor. Also, since K3D ships with a bunch of stuff enabled, I disabled anything that wasn't required to optimize its performance. Let's execute the test. And here are the results. As you can see, anything running on Docker Desktop is a bit faster. Also, it's clear that K3D is exceptionally fast. MicroK is quite a bit slower than the others. This is caused by it downloading a lot of content every time. What's a bit odd is that Minikube seems to be quite a bit faster on Docker Desktop than on Rancher Desktop or Podman. In conclusion, I think I prefer the convenience of Docker Desktop and Rancher Desktop. Having a reset button on the UI is just really easy to use. However, if speed matters, then K3D is the choice. And that also is the perfect transition to the final challenge, because there's a particular place where speed matters the most. Challenge number 6. Usage in continuous integration. Speed matters in CI a lot. In this final challenge, I want to find out how each Kubernetes offering fares. I've built a GitHub Actions workflow to find out. As you can see, I'm comparing K3D, Kind, Minikube and MicroK. Rancher Desktop and Docker Desktop are out of the race because they are desktop apps, and Podman is out because GitHub Actions offers Docker as container engine already out of the box, and an additional one is kind of unnecessary then. The code is in the description, so here's just an overview. I create a cluster, install a workload on it, and finally I check via curl that it responds. To create the clusters, I'm using a different GitHub action for each solution. Without further ado, here's the numbers. As you can see, K3D takes the cake. It's blazingly fast. The numbers you're seeing here are the average over 20 runs each. Let me quickly explain why K3D is listed twice. We've seen in Challenge 4 that K3D supports services of type LoadBalancer. I deployed both type NodePort and LoadBalancer to see if there is a performance difference. And there is, but it is very small. All the others use type NodePort. The conclusion here is that K3D is significantly faster than its competition. Comparison. Now that we've seen all these solutions in action, let's round them up in a big comparison table. And I'm telling you, it's going to be quite the table. Let's get started. First, built-in Kubernetes. All the solutions with the exception of Podman offer built-in support to create a Kubernetes cluster. Podman is however able to run the container-based solutions Kind, Minikube and K3D because it is a container engine. Next, GUI versus CLI. Every solution except Docker Desktop offers a CLI to manage clusters. Rancher Desktop is, however, most similar to Docker Desktop because it is GUI first and its CLI feels more like a passion project. Now let's compare when each project had their initial release. We can see here that Docker Desktop and Minikube have been around the longest since 2016. Minikube's GUI is, however, only a few weeks old and Podman Desktop only a few months. Most of the projects have a bigger organization behind them. For Docker Desktop, it's Docker Inc. For Rancher Desktop, it's Rancher Labs, who have been acquired by SUSE in 2020. Minikube and Kind are Kubernetes special interest group projects. Microcates is from Canonical, who are well known for their Ubuntu operating system. Podman has corporate backing from Red Hat. Only K3D is a project by an individual without corporate backing. I should mention here that both K3D and Rancher Desktop use the Kubernetes distribution K3s under the hood. License-wise, every project is licensed under an open source license, with Docker Desktop being the only exception. Its license model is largely free as well, but you need a paid subscription if you're using it for work in a company that has more than 250 people or $10 million in annual revenue. Next, the number of GitHub stars. This number is a vague indicator to gauge the popularity of each project. Alright, and the rest of the table will be feature comparisons. First, there's Docker CLI support. We've seen in Challenge 2 that Rancher Desktop, Minikube and Podman can serve as replacements for Docker Desktop. The Docker CLI, which is just a client, works with them as well, and you can run containers and build images. Second, K3D, Kind and Microcates have support for multi-node clusters. I didn't cover this in this video, but it's there if you need it. Next, CI usage. Everything except Docker Desktop and Rancher Desktop, which are desktop apps, is suitable for usage in CI, but K3D is clearly the fastest. Then built-in metrics server. Everything except Kind and Docker Desktop offers it, either by default or via an add-on. Next, a way to select the Kubernetes version. I wish Docker Desktop let us choose which version we want. Furthermore, a built-in Kubernetes dashboard. Rancher Desktop and Minikube offer a dashboard out of the box. Also, Microcates offers a dashboard add-on. The others don't offer a dashboard, but installing the official Kubernetes dashboard manually is always an option. Then, whether registry mirrors can be configured to avoid having to re-download images when recreating the cluster. For Docker and Rancher, it's not necessary to re-download when restarting. For Minikube, only a mirror for Docker Hub can be configured, and K3D and Kind are fully configurable. Next, whether it's possible to have more than one cluster created at the same time. K3D, Minikube and Kind offer this, the others don't. And finally, whether there is support for services of type LoadBalancer. We saw this in Challenge 4. Docker and Rancher Desktop and K3D offer this, the others only conditionally. That's it for the grand comparison table. Let's do another final and smaller table for just the 4 desktop apps. Talking UI look and feel, in my opinion, Docker Desktop is the clear winner. Its UI is just rock solid. It's snappy and it looks good. Rancher Desktop's UI looks good and is very organized. It could, however, really load a bit faster and without the white flash. Minikube's UI is functional and fast, but it definitely lacks design. The project is only a few weeks old, we just have to see how it develops. Podman Desktop's UI looks really nice. It did, however, sometimes get a bit unresponsive during my testing. While it gets today only 3 stars, I have to say when browsing through the design mockups that the team evidently has great plans. If they actually can pull them off, they'll end up with a seriously slick piece of software. Next, start in background add login functionality. Note that the in background is key here. All but Minikube GUI have it, and at Minikube they have an open GitHub issue for it. Well, since 2019, I guess. Finally, whether opening and exiting the app starts and stops the container engine VM. Docker Desktop and Rancher Desktop have this feature. What's great about it is that there's always a clear indicator in the status bar whether Kubernetes is running or not. Podman Desktop seems to sometimes but not always stop the VM when the app exits. Recommendations. We are coming to an end here. Here's my final verdict for what I recommend. For local development, I recommend using Rancher Desktop or Docker Desktop. Each has their pros and cons. I won't repeat the details because you've seen that there's lots of them. But essentially what I like about them both is that they're easy to use desktop apps with a GUI. This makes them beginner friendly, and also experts benefit a lot from having an icon in the status bar indicating the cluster status. One decisive factor between them could be Docker Desktop's license model. For CI usage, I recommend using K3D because its performance is unmatched. A solid alternative is Kind, which is a tad slower but also quite good. Alright, that's the video. If you'd like to view the code used in this video, I've put a link down in the description. Did I miss a solution that you like? What's your experience with running Kubernetes locally? Leave a comment below. Hit like if you learned something. Bye.